Hi, this is Traxi Computer Science. We're looking at part 4, which is GPU computing. Initially, GPUs were invented for gaming, and that's how the graphics processing unit came into picture. And NVIDIA was focused on generating or helping gamers solve a lot of matrix multiplications. And later, when neural networks came into picture with AlexNet, ImageNet, and everything, NVIDIA saw that hey, there is a lot of computations going to happen, so they double down on their efforts on improving AI using GPUs. That's how GPUs were born initially. But today we are going to look at what are GPUs, how is it computed for compute, how it is calculated for various needs of AI. We are going to look at CUDA in short. Then we are going to look at GPUs alternatives, which are TPUs and NPUs. Remember, GPUs are machines that are doing most of the compute or heavy lift behind the walls, and it's the single largest line item that AI product managers need to consider when looking at the infrastructure, the cost, and so on. GPUs are typically like a white calculator that are sitting behind a narrow memory pipe, and if there is not enough data provided, the calculator is going to sit idle. That's what we are going to look at. So let's deep dive. Imagine an infrastructure team comes and says, hey, we need 60 more H100s. First thing that you need to ask for is, hey, how did you come up with that estimate? So adding more GPUs might not provide the right performance improvement, so we need to ask for this arithmetic. Modern GPU is not primarily a fast calculator. It is a very wide calculator that does faster multiplications or operations on matrices. What needs to be done is we need to provide it the right amount of calculations for it to perform at the peak, or the whole pipeline to perform at the peak. And that's why we are saying, hey, hardware is not an implementation detail, because this sets your latency floor, it sets your context length, cost per token, or peak traffic ceiling, which is number of tokens per second, your leverage with a cloud vendor, how much are you going to negotiate for the pricing and everything. And there are certain constraints that will be dependent on the type of hardware that you're choosing: memory capacity, memory bandwidth, compute, and interconnect. Yeah, we are going to look at all of this. Ultimate objective is that you are able to challenge a GPU procurement ask from the procurement team with utilization math. Yeah, that's what we are looking at. And five terms that we need to understand from the beginning is flop, which is floating point operations, and floating point operations per second. So this is a rate at which the operations are being performed at a per second. So it could be or which is trillion flops per second, p flops, which is quadrillion flops per second. High bandwidth memory, it is the memory that is sitting closest to GPU and provides all the required calculations that GPU needs to perform. So if you don't pass it enough to GPU, the GPU is going to sit idle. If you provide it too much and there is no compute to be done, even then the performance will be sealed. So we need to understand how much capacity can that GPU take, or high bandwidth memory can provide. At the same time, look at the bandwidth also. How fast can we provide the number of bytes to the GPU to process? So it is like warehouse size versus conveyor belt. Both have their own limitations separately, but when combined together, the optimization is that, hey, based on the warehouse size and conveyor belt, you provide the right number of elements to be processed. Kernel is a small batch of program that runs on the GPU. So fusing kernels keeps this intermediate results in fast memory instead of writing them back out. So HBM does all of that. One thing that we're going to look at it is the arithmetic intensity. It tells us that how much work is being done on the per byte that is being fetched from the HBM. It could be low if there is little compute and lots of data movement. This is what we discussed about. If there is so much data being passed on, but little compute is happening, it means we are memory bound. If it is high, arithmetic intensity is high. If lots of compute per byte is being done, then we are compute bound. We need to improve the size of the compute or GPU. Utilization, this is how we calculate utilization. Ideally, it would never be the same number that vendors are proposing. It would always be less than that. And when we do some calculations in this session, we will understand why it is always less than that. Okay. And this is the mental model that we need to have when thinking through how GPU and high bandwidth memories work together in sync. Imagine there is a stadium of school children. They are ready with calculators, or they are ready to do some arithmetic manipulations. And HBM is a warehouse where you have stocked all the worksheets that need to be passed on. And imagine there is a small entrance to the stadium. So how many worksheets can pass through this memory bandwidth to, or through the tunnel to the stadium, will tell us how much output can be gotten or got from this system. And this is purely dependent on this tunnel bandwidth. If more can be passed, more compute will happen, all the students will be occupied. But if not sufficient worksheets are passed through this tunnel, some children are going to sit idle. This is the whole context framing for this session, which is high bandwidth memory, which has a lot of memory that needs to pass on the required compute to the GPU. If enough compute or number of bytes is not passed on, GPU is going to sit idle. Even if you pass more, GPU will be blocked because there is only enough compute you can do. So 6 parts from why GPUs to a defensible procurement number. That's what we're going to look at. We're going to first understand why we need GPUs in the first place, parallelism, SIMT, and the shape of a matrix multiply. We can look at it. We would look at it, the memory wall. How do we hit the ceiling? The software stack, CUDA, the mode, and why alternatives struggle, which are CPU, TPUs, NPUs, and so on. Inference economics. We are gonna look at prefill versus decode, cache batching, quantization techniques to improve the inferences. We are going to look at alternatives like TPUs, CPUs, AWS, AMD, and other systems. Finally, the drill would be that you go and challenge a GPU procurement task with utilization math. SIMT stands for single instruction multiple threads. It is a parallel computing execution model used in modern graphics cards, typically like GPU. So multiple instructions are batched together as threads, and they are sent to GPUs to execute. CUDA is the compute unified device architecture built by NVIDIA. It is primarily for parallel computing platforms, and we will read more about this. KB cache is all about key value cache. We looked at this in the previous parts across other tracks as well. TPU is tensor processing unit, NPU is neural processing unit, A6 is application specific integrated circuits. And it's right to ask, hey, in the world where CPUs were ruling the roast, why did GPUs win? I believe it's a simple math, because neural networks were doing a lot of compute, they were learning a lot, and we needed the compute to happen a little faster. And it was simple that neural networks were nothing but matrix multiplications, and underlying GPUs was a simple concept that matrix multiplication is nothing but parallel simple computations. And they built, our GPUs were primarily built as a hardware for that. So we looked at this in previous sessions as well. The workload is nothing but a matrix multiplication, and it is embarrassingly parallel, as in a neural network would have 70 billion parameters, and all of those parameters when needs to be multiplied, which is the incoming token or input context, we need to do nothing but multiply and add operations on top of that, weights, and with no dependencies, because these were independent calculations that need to be done. CPUs were optimizing for the opposite. They were good for sequential and branch heavy, because if you had too many if then else conditions, they would do this. And they were latency sensitive threads, as in they needed to be executed in sequence in the right forms with big caches and speculation. Then CPUs were good, but GPUs made the other trade. They said, hey, if there is simple arithmetic calculations that need to be done, we will do that with simple or minimal control logic and enormous memory bandwidth, which is coming from your HBM, high bandwidth memory. As an example, H100 class GPU has around 16,000 CUDA cores plus dedicated tensor cores. Yeah, that means you can achieve uh, thousands and millions of floating point operations, which helps you do the bulk of training of large language models and inference. First thing that we need to understand is single instruction multiple threads, which helped us execute so much on these GPUs. Yeah, especially in NVIDIA's case, a GPU takes groups of 32 threads into a collection called warp, and these threads execute on the same instruction collectively. Yeah, two consequences drive this real performance. Branch divergence is very minimal. Yeah, that is, if then else conditions are not really there. Yeah, they are very minimal. If they take it, the branching happens and the compute will be sitting idle. Yeah, as in wasted cycles. The compute is not fully used. So more conditional logic inside a GPU typically reduces the throughput. Coalesced memory access, we saw this in previous sessions as well. If 32 threads are not having the memory adjacent to each other in the addresses, then GPU will have to fetch them from different places, and that scattered memory multiplies the number of transactions. This also will result in a lower throughput. So coalesced memory access means all the addresses are adjacent to the next one or each other. In that case, the performance is pretty high. And floating point operation is another ladder that we need to understand. If we are looking at what do we mean by floating point operations? Okay, matrix multiplications are happening on not integers but floating point numbers, and in that floating point numbers, the precision or decimal places is very important. If each number is represented by floating point 32 bit representation, which is basically 4 bytes, the compute will look different versus a floating point 8 bit precision, which is 1 byte precision. Yeah, here the precision is pretty high compared to here, which is required for lower precision tasks and so on. Yeah, also it could also mean that we have taken high precision LLM model and quantized it into a lower precision for certain tasks. So let's look at where these are used. If it is floating point 32 bit operations, which is 4 bytes per value, this is all about legacy training, some accumulation and scientific computings, because precision is required. TF32, where 4 stored and reduced mantissa is used, there is a reduce or a drop in the speed up for FP32 training on tensor cores. I do not understand what this is. I believe we need to drop this line. Floating point 16 bit, which is 2 bytes, typical standard training and high fidelity inferences. Many of the LLMs that we see today are on floating point 62. Yeah, FP8 are 1 byte per value, which is Hopper and later, increasingly standard for large model training and serving. These are quantized inference models. They have big savings. They require certain calibration and quality evaluation because you dropped the floating point by 1/4. Yeah, so a quality evaluation is required, but they are typically used for classification tasks, summarization tasks, and so on. The rule to memorize is having the precision roughly halves the memory footprint and roughly doubles the memory bandwidth limited throughput. So this is talking all about this diagram. Yeah, more memory, the better the bandwidth, the higher the GPU, the better the calculations. And that's what we are talking about here. You halve the precision, roughly halves the memory footprint, which is HBM. In high bandwidth memory, you are reducing the total memory footprint and roughly doubling the memory bandwidth limited throughput, because now there is half the floating point size. Now you can literally double the bandwidth of data or byte data that's passing through that tunnel. Yeah. So quantization is typically a throughput story, not only a fits on a smaller card story. So typically whenever people say quantized, they think about, hey, I need since I've quantized, now I can fit the model on a smaller GPU. That's part of the story. The other part of the story is that it's a throughput story. So this brings us to the second topic, which is a memory wall. Yeah, we looked at the diagram. On the right side we had HBM, which is high bandwidth memory, and in the center we had the tunnel. On the left side we had our GPU. Yeah, capacity answers, hey, does the model fit, or the GPU on GPU, can that model, a high bandwidth memory model, can be brought onto the GPU? Yeah, how much? And bandwidth answers, how fast can I read it, how fast can I send the data? Yeah, that's what we are going to look at. So imagine and these are approximate 2026 figures on certain GPUs that we have looked at. So imagine A100 80 GB. What we are saying is, hey, it has a 80 GB HBM capacity, high bandwidth memory capacity, and its bandwidth is 2 terabytes per second, which means using BF16, which is floating point 16 calculations, we are looking at 312 T flops, which is trillion flops calculations. And we are going to look at how this impacts our token generation as well. Yeah, but if you look at it from 180 to 140, yeah, the bandwidth rarely moved, but your memory capacity has almost doubled, nearly doubled. Yeah. So what we are trying to say is, at some point in time, the bandwidth will hardly improve, but your HB capacity could be doubled. Yeah, and here you see it grows further with this, and the numbers that promise you are totally different from what actually happens in the real world. And if you were to look at arithmetic intensity and the roofline that we would typically reach, this is how we need to calculate it. Arithmetic intensity, we always saw that it is the number of operations being done by the GPU with the number of bytes being moved inside. Yeah. So this is the true performance of a GPU. Yeah. Balance point is that, hey, you have peak flop operations being done for the peak bandwidth. For example, if you say 990 T flops for a 3.32 terabyte, it is approximately 295 flops per byte. This flops per byte helps you understand the token generation capacity of the GPU based on the high bandwidth memory, the memory bandwidth, and the GPU. How? Let's take a look at this. Imagine you are getting 295 less than 295 flops per byte. It is basically meaning memory bound. That is, you're not doing enough calculations. Sorry, you're not passing enough bytes per second. The or you are passing too much data and it is not able to compute. Yeah. So moving data seems to be the bottleneck here. Example, single sequence token generation. Decoding will be slower. If it is greater than 295 flops per second, it means compute bound. We are sending so much data, too much data, but the compute is not happening more. So it basically means that we have reached the limit of the GPU in this case. So arithmetic units are the bottleneck, large batch training where the same weights are reused across many examples. The same. So what we're trying to say is the performance rises with memory bandwidth until it hits the compute ceiling, which is GPU. Which side you are on decides whether we need more flops or more bandwidth actually helps. So that's the whole conversation here. How do we hit the roof line? Because of these two: bandwidth and the compute. Memory, compute. Large batch training is usually compute bound. This we know very clearly. Single sequence generation is usually memory bound, so adding flops does nothing for it. So if you are generating tokens in sequence, it doesn't matter, yeah, how much memory you pass, it's still going to generate all the data in sequence. So compute is not the challenge there, it's memory. Whereas when we do training, in training we are passing so much data in parallel, we are trying to compute hundreds of thousands of transactions. The bandwidth is high, but there is only a limit on GPU, and that's why it's a compute bound. So training is typically compute bound, inference is typically memory bound. Imagine, let's take an example of how we are hitting a 24 tokens per second ceiling. Yeah, imagine there is a 70 billion parameter with a floating point 16 operation model, so it's 2 bytes, 16 you know, and 70 billion into 2 bytes is approximately 140 GB of weights. That much GB of weights we are gonna compute. H100 has a bandwidth of 3.35 terabytes per second. So your total GBs per second are terabytes per second, which is 3.35, which we saw earlier, divided by this 140 GB. That gives you the number of passes that can happen through the neural network, and each pass typically generates a token. So what we are saying is there is a theoretical ceiling of 24 tokens per second before attention, kernels, and scheduling, which are other topics that consume other type of memory. So why are we saying this is slow? To generate one token, the GPU repeatedly reads the entire model's weight from the HBM while doing little compute per byte. This is very low arithmetic intensity. So much data is being passed from here to here, but not many calculations are happening here. So this is very low arithmetic intensity. And this is the problem with single user LLM inference. Everything is happening in sequence and enough compute is not being used. Multi-GPU and interconnect. We saw this data parallelism, tensor parallelism, pipeline parallelism, and expert parallelism. We saw all of this in previous sessions. Okay, maybe we'll go through this once more. Yeah, data parallelism is all about every GPU holds a copy of the model and executes on multiple different set of data. What this helps is it syncs gradient each step, needs the model to fit on one card. So we need to ensure that if we are taking a 30 billion parameter with 2 bytes, it's approximately 60 GB. So it can fit on a 80 GB GPU. That's how we see it. Tensor parallelism. One layer's matrices are split across multiple GPUs. This requires a very high bandwidth within the layer. It would need some good networking links like NVLink, yeah, within one server where there are multiple GPUs. Pipeline parallelism, different layers on different GPUs altogether. This is a cheaper communications happen, but the pipeline itself bubbles because there are idle stages. Some of them will be waiting on others to complete and so on. Expert parallelism, mixture of experts on different devices, tokens routed. This is a routing traffic problem. Our communication between experts needs to take place. So different strategies provide different communication styles. And that brings us to that software stack. While we have the GPU, high bandwidth memory, but everything rests on top of that, which is a layer called software stack. And CUDA, which is compute unified memory that was built by NVIDIA, is a huge moat for them because it's a library that's very hard to replicate now. And they had started this around 2011 2012, almost 15 years of compounding growth on that has produced kernels that are hard to port now. Yeah, so CUDA, like we said, it's a compute unified device architecture. It's a parallel computing platform and programming model. So it has a set of libraries that builds a C++ dialect, a compiler, a driver, and a mature ecosystem of highly optimized libraries. Yeah. So these libraries ensure that when you do your neural network multiplication, everything, they are passed on through these libraries to the underlying GPU for multi-processing of those matrices, where GPU computes and gives back the responses, and these CUDA libraries pass on that data back to the system. So a bunch of libraries were developed, like QBLAS, which is CUDA's basic linear algebra subprograms. This is for dense matrix and vector operations, optimized heavily for GEM, which is general matrix multiply. Yeah. DNN, the deep neural network library that was built, NCCL, which is NVIDIA's collective communications library, CutLAS, which has templates for linear algebra subroutines. So while even I am not aware of this, one thing that I understand as a product manager is these are the libraries sitting on top of the GPU that help you compute the instructions that are being sent and pass it in the right format to the GPU to compute. Yeah. Yeah. So flash attention was one example that was built, an attention implementation that reorders the computation so intermediates stay in the GPU's tiny fast SRAM instead of round tripping to HBM. So intermediate values are being still stored in SRAM instead of sending it back to HBM, which is high bandwidth memory. Yeah, this provides large real speed ups. Yeah, zero change in the mathematics. So the whole course's principle is in one library. You optimize memory movement, not arithmetic, because arithmetic has a ceiling, but the memory movement from HBM to the SRAM is something that could be improved, and that has provided the compounding benefit of performance. And why this moat holds is they have built this over 15 years of kernels, the compiler maturity, and every research artifact on GitHub is written for CUDA first. So porting this is possible, but the tail of small ops and custom kernels is where the projects die. So not many people are trying to build this from the scratch. What we are currently trying to do is optimize them further, take them further, and really improve. Yeah. And there are other libraries as well, but they aren't as good as this. And this brings us to chapter 4 of Traxi part 4, which is inference economics. So how do we calculate how much does it take to infer a single token? And this is important because the number of requests that we get from our customers or users as product managers is what we will use as a base to calculate the number of tokens that are required to serve them per second. So prefill versus decode. Prefill is more like training, yeah, where you are taking the prompt and processing it, setting the context. Decode is where you actually generate the tokens. So here all the prompt tokens are processed in parallel, one pass. So compute is the limitation here, whereas in token generation, memory bandwidth, because you're only passing one token at a time, or a context, only one token is being generated. Here it's a memory bandwidth. Our compute is being wasted here, I would say, rather than it saying memory bandwidth. I would say compute is being wasted. Parallelism high, because you could write the whole prompt at once and punch it, but here it happens in a sequence. You are generating one token at a time, and it is if you were to measure prefill, it's all about time to first token, because you're giving this whole context, and until the token generates, it's all about processing the prompt. So time to first token is the metric here, whereas here time for per output token, how much does it take to generate every token, or in total how many tokens per second is the metric that we could use to measure the decoding process, yeah, generating token process. If this scales with prompt length, yeah, it's quadratic in attention, but this generates linearly because it depends on the output length. If there are 4,000 tokens to be generated, and the system is generating 40 tokens per second, it is linear in nature, and it will take maybe 100 seconds to do that. But if there are 8,000 tokens to be generated, then it will take, instead of 100 seconds, it will take 200 seconds to generate it. So what we're trying to say is it purely depends on the output length, and it's very linear in nature. The KV cache and other things that we have not considered earlier also need to be considered, because ultimately these lead to the total performance of the system. Yeah. And how much kv bytes are we going to consume, that will depend on 2 into the number of layers of llms into kv value heads into the dimension head dimension, sequence length that we are generating. It could be 100, 200, 500, in thousands also, into the number of batches that we are trying to process, ultimately multiplied by the bytes per value. So much compute needs to be taken into picture. If we are looking at 70 billion parameter model, you know, there were 80 layers and 8 kv heads, which is gqa, which is group query attention, and the head dimension is 128. It's a floating point 16 size matrix values. Then per token sequence is, if you say 0.33 MB, then 32k context, which is in k bytes, will be 10.5 GB for one user, and we have not multiplied this with the number of users. 128k context will be approximately 42 GB. So what are we trying to say? We are trying to say that, hey, a single user at 128k context eats tens of GBs of the memory we wanted for batching. Yeah. The cost of long context is not arithmetic, it is memory occupancy that blocks those users. So if there is no enough HBM, which is high bandwidth memory, in terms of GBs, we are going to be stuck. Yeah. So if you send the same 4,000 token system prompt every time, we are wasting memory. So what we need to do, memory cache it or prompt cache it, yeah, is often the cheapest win. Whether ask whether this is enabled if frequently it is not used. Batching is another layer we looked at in one of the earlier sessions as well. Hey, instead of saying one sequence weighs one token, which is waste of compute, we could say 64 sequences can be sent in together to read the weights. Approximately 64 tokens can be generated. So this is purely memory bandwidth. How much memory can we pass on? And one sequence weighs this most compute if you put it in sequence. But if you put it in parallel, the bandwidth would be high. We could do a lot more compute. So if you are starting to do something around training and inferencing, and you understand that it's bursty and low traffic, always it's in small batches, then it typically would lead to poor utilization and there will be high cost per token. But if there is steady high traffic, then it means large batches, high utilization, and low cost per token, because there is so much being generated. It's not bound by compute, but rather by the memory. So cost per token depends on utilization, and utilization depends on traffic patterns. So if it is more stable and high, it will be low cost per token. If it is very bursty and low traffic, there will be high cost per token. MFU, the model flops utilization, tells the same. That's the number we need to watch out for. We also need to understand that this model flops utilization is actually a fraction of the hardware's theoretical peak, because when they compute them, the numbers quoted on the SKUs or rate cards actually are theoretical peak flops, not the actual ones. The best case, we could get a performance of 35 to 55% of actual MFUs, which is model flops utilization. Because much of this memory goes into other tasks, your KV cache and other stuff. So the sentence that is most of the drill is, anyone who plans capacity at 100% is planning to fail. So we need to consider realistic utilization, which is 35 to 55% of the GPU. And not just GPUs, right? There are alternatives as well. this is where companies are now competing. uh, uh, Meta try to build their own chips. Anthropic is trying to build their own chips now. um, Grok says they will tie up with Nvidia initially. They might plan for their own chips also. AMD is a good competitor. We have Google building their own layers. So it's a workload economics decision, because the more compute somebody can deliver for the same GPU, everything built around that also needs to be optimized for that, and that's why alternatives exist. So TPUs, which is tensor processing units, are one such systolic arrays, uh, which work in a little different way and are tied to the Google's ecosystem. Yeah, when we say Google's ecosystem, all their chips, everything cloud model, everything is done there. In a real, as a real strength, they have a very stronger performance per dollar and per watt of large dense workloads. So they are pretty good, but the problem is that we have to use Google Cloud only for that. Accelerated linear algebra prefers static shapes. So if there is something that's not changing much, using Google Cloud and Google's TPUs is the best way. It's faster, high performance compared to even GPUs, and it has a smaller ecosystem than CUDA, because CUDA is supported by a lot of open source developers as well, and it uh, it really does the job. So if you are considering the best alternative for GPU, it's purely TPU. Yeah, they provide the best alternative infrastructure path as well. The only challenge being they have a deeper dependence on Google's ecosystem. NPUs, which are neural processing units, they are also good, but these are for edge devices. So for AI accelerators in phones and laptops, these are really good, and there are multiple companies that provide NPUs, and they have the objective as maximum useful AI compute per watt, not peak throughput, because battery usage being slowed down using AI is a big hurdle, and it needs to be very economical in nature. On device changes the economics, because there is near zero marginal inference cost. The battery belongs to the user. There is no network trip round trip happening. There is this purely offline capability. The data stays on the device, which is privacy friendly and predictable latency, because there is no network layer here. The challenge being its limited memory capacity. The compute is limited. These are smaller models in the first place. Device fragmentation, too many devices to be tested on. Battery or thermal limits. Battery could heat up if more compute is used. It's harder to update these models once it is deployed, and there is no, literally, zero to little limited observability on this. Cloud Silicon Inference ASICs, which is application specific integrated circuits, these are there in the market, but primarily for specific use cases. So the more specialization you have, you need better performance for specific workloads, then you go for these inference ASICs. uh, the challenge is it has less flexibility across workloads, so these are built for very specific types of workloads, and this could really help them. And that brings us to the engineering drill. At the beginning of this session, we said, hey, if there is the infrastructure team that comes and says, hey, we need 64 GPUs of H100s, how do we answer it? Yeah, if somebody says we are at a capacity, how do we handle that situation? What we need to do is we need to treat this as a problem that needs arithmetics or calculations. Yeah, we need to force the translation into numbers. So if there is a demand that needs to be coming in, we need to understand the memory and the throughput. Yeah, how much replicas are required, and understand the utilization also, because then all of this will help us understand the procurement requirement in the first place. So if there is a 70 billion model which has a 16 floating point, we are looking at anywhere between 70 billion into 2 bytes, which is 140 GB of weights. The memory itself requires 140 GB. One way H100 can only store 80 GB of data, which we saw. It cannot hold 140, so approximately we would need 2 GPUs or tensor parallelism. Yeah, so 200 which is 160 high bandwidth memory minus the 140 GB weights, which is 20 GB left, which is not free memory. This would be used by context memory. This could be used by KB cache and other types as well. And if you were trying to generate 8,000 tokens at 7 concurrent 8,000 token sequences for 2 GPU replica, that would mean that the replica would run out of memory before it runs out of compute, because we are exceeding the total size, which is 160 GB. And hence we could ask for additional compute or memory. How? So we need to calculate the demand. Hey, there are 1200 concurrent requests coming in, where our system can do 40 output tokens per second, so which is 25 millisecond per token generation target. If we keep it, we are looking at 40 output tokens, which is 1 by 25 milliseconds, which is 40. Then we look at 48,000 tokens per second requirement. Yeah, so that's 1200 is product, 48,000 is infrastructure requirement. Now this is the demand side. How do we supply this? Yeah, we need to ensure that if there are two 800 replicas which generate around 900 tokens per second under the actual workload, we could divide this 48,000 by 900, which means 54 replicas. Each replica would have at least 2 GPUs, like we saw earlier here. Yeah, we were using 2 GPUs, and in that case 54 into 2, which will be 108 GPU requirements. Now this means we are trying to calculate the supply or new requirement based on the exact demand. Now this is a defensible number, not a guess. Instead of user coming and saying I need 64 GPUs, now we have a pretty precise calculation saying 108 GPUs, and it's based on the peak demand, 1200 concurrent requests. Ideally we should have a little more than this, just to ensure that stress loads are managed. That's what we are saying. Before buying 32 more GPUs or 64 more GPUs, we need to ask these 8 questions. Utilization. Are we using it completely? If GPUs are at 12%, there may be no compute shortage, just bad batching, scheduling, routing, or memory allocation. So we need to improve this. If we do continuous batching, the system would improve for utilization. Prompt caching. We could ensure that the prompts are cached, and you could save some memory there. Context distribution. So provision for these percentiles, not for the 32k max. Yeah, longer context would mean bigger kb cache, means smaller batches which are happening in parallel, which would mean a higher cost per token. We remember, if you remember this, we discussed earlier, smaller batches means higher cost per token. If it is higher number of batches which are in parallel happening, then it is lower cost per token. Quantization. We could quantize the whole model and double the whole input. So instead of needing 108 or 110 GPUs, we would now need a lower GPUs. But that needs to be gated for quality evaluation, because drop in floating point size would mean drop in precision. Drop in precision would mean varied answers. So we need to really look at it from the angle of quality. Does this every request need 70 billion parameters? Need not be. Maybe we'll have smaller models that do that task. So that's a more product architecture decision. It's not a GPU tweak that we are looking at. Peak versus average. Are we really looking at peak versus average versus percentiles? for for what are we buying these 32 more GPUs? Buying for 4x peak leaves approximately 75% idle. Yeah, so we need to understand how much percentiles are we trying to achieve. Forecast versus reality. Is 1200 measured or assumed? Is it true actual market behavior, or what is it? If the current peak is 700, buying 100 GPUs is actually spending on a guess. And this is how we need to word it in the final call. Hey, we don't need 108 GPUs because we are guessing. Yeah, but we need to say that, hey, at the current measured serving efficiency, our modeled peak requirement is 108 GPUs. Before committing, we will validate the batching, caching, the context distribution, quantization, and model routing, because this will peak the current architecture's performance. Yeah, and then each optimization will get a measurable baseline, target, owner, and production benchmark also. Yeah, we then reforecast using real telemetry. So we need to optimize for these first by taking ownership, and then look at what is the new requirement. And that is the difference. Before approving infrastructure on dollars, we are doing proper infrastructure management, product management. We are saying, hey, at capacity needs to be identified first through demand. We understand the memory requirement with a measured throughput. We understand the required replicas. We'll calculate the utilization. We'll optimize the opportunities. Finally, give it to the procurement team, identifying the demand supply gap. And that brings us to the interesting PM perspective session, because here we understand, hey, why is this required for a product manager to understand? Yeah, and any misconceptions that we might need to avoid. We need to remember that as a PM, we need to understand that, hey, these are hardware sets or products physics. Yeah, the latency floor, max context per token, the concurrency ceiling, all downstream of memory bandwidth and capacity. From HBM to GPU, whatever happens beyond that, everything sets the product's limitations. It is usually the largest variable cost. Bringing in additional GPUs might solve the problem, might not solve the problem, but every time we bring that GPU, it's the largest variable cost that we are putting in. Yeah, it is where the infra's credibility is won. Absolutely, because we are saying, hey, is this a compute bound problem or a memory bound problem? If we understand that, we can take the required fixes on top of that. It shapes the strategy. Do we do on device versus server, single versus multi vendor, self hosted versus API? All hardware questions, literacy questions, needs to be answered before they are business questions. Yeah, misconceptions that we need to avoid are, more flops means faster inference. No, there is there is something called memory bandwidth as well. Yeah, decode is memory bound. Extra flops often changes nothing. Compute increasing just the compute will not solve anything. 90% utilization, so we need more uh, uh, the model flops utilization or max flops utilization. We need to understand that 90% utilization is very high. At the max, we would achieve 35 to 55%. If improved, maybe to 70%. Quantization just saves memory. No, it also changes the throughput or output. So you need to ensure that proper evals are put in place, or quality evaluation is put in place to ensure quantization doesn't put out wrong answers. Bigger context is a software engineering problem. No, it is a hard KV cache price that shrinks your batch. Yeah, self-hosting is always cheaper. No, it depends on the usage or utilization. Yeah, only above sustained high utilization, self-hosting will be cheaper. We are logged into NVIDIA, weak for inference of standard models by LLM. Test it. So you use other models to do other tasks which are not quality intensive in nature. Here are some interview questions that could be asked. Hey, why is generating tokens slower than processing the prompt? Because processing the prompt is parallel and generating the tokens is sequential in nature. different workloads. Yeah, there are different types of workloads. Prefill processes every prompt token in parallel, saturating the arithmetic units. So this is more compute bound. Decode generates one token at a time, each reading the entire set from HBM, which is high bandwidth memory, for approximately 2 flops per parameter, which is very low arithmetic intensity. So it is memory bandwidth bound. Yeah, and the chip idles on memory. So it's not compute problem, it's bandwidth problem here, or memory problem. It's not a compute problem. So we are at capacity, we need more GPUs. What do you ask? Hey, understand the demand first. Which resource is exhausted? Capacity, bandwidth, compute, interconnect. Which of them is maxed? So we need to understand that. Then measure model flops utilization and memory occupancy. Then the efficiency layers before capital. We need to improve all of this: continuous batching, prompt caching, prefix size, real context distribution, all this. Try to do context quantization evaluation also, and routing easy request to a smaller model. If all of this does not improve, then go to additional GPUs. Until then, do not do it. What is KV cache and why should a PM care? Yeah, we know this, that when model tries to generate tokens, it needs to look at all the previous tokens. So looking at previous tokens and regenerating them every time costs much. So what we do, all the previously generated tokens are stored in a memory, cache memory, which is key value cache memory, for every token that it tries to generate, so that it does not recompute them. Yeah, and this lives in high bandwidth memory. As the weights and grow, as the weights and it lives in HBM, and it grows with the context length and concurrent users. And that's why group query attention, paged attention, and prompt caching exist to solve that problem. When would you put a model on device instead of the cloud? We saw this, when latency, privacy, or marginal cost dominate, and the task fits a small model. For example, next token prediction or typing token prediction, all that are simple on device that could be built. Anything that costs or requires high precision and so on, we will need a server to solve the problem for. Cost per token doubled after a launch that tripled traffic. How? Almost suddenly a change in traffic shape, not volume. Cost per token is driven by batch efficiency, which depends on instantaneous concurrency. Spikier traffic, a new underutilized region, or a segment sending much longer context, each lowers useful work per weight load. And we saw that smaller batches typically means high cost per token. Yeah, so we need to improve the number of batches that are being sent. Long contexts are the likeliest culprit. So a bigger KV cache per user shrinks the batch, as in reduces the batch size. So per GPU throughput falls even while GPU looks busy. So break cost per token down by region, the context bucket, and the segment. Look at the batch occupancy over time. Yeah, the fix is usually routing or consolidation and not more hardware. 8 things that we need to remember is typically this. Memory bandwidth, not floating point operations, typically limits the token generation. So we need to have high bandwidth as well. Prefill and decode are different workloads for different fixes. Yeah, with the different fixes. The KV cache is why long context costs money, because the higher the size, the higher HBM needs to be, and it's sequence in nature. And every time we have to pass the KV cache back to the flops to generate the next token and so on. So batching is a primary lever on cost per token. So batch as much as possible to reduce the cost per token. And model flops units is the utilization number, and it is low. Yeah, it is always low. It is not fully utilized. All the GPUs are not fully utilized. Quantization is a throughput lever, not just a capacity lever. We just saw this. When you do the quantization, the number of bytes that you can pass through from HBM to GPU also increases. Not just the size of memory. So match parallelism strategy to interconnect or waste the hardware. So we need to look at these parallelism strategies as well. Do you do data parallelism? Do you do context parallelism? Do you do a GPU parallelism? What do you do? Never plan capacity against peak spec sheet flops. So it always needs to be in percentiles. That brings us to a closure on track C part 4, which was GPU computing. If we had to take away one thing, it would be this: a data movement problem is a compute problem's clothes, it's not the truth. So if you have to look at the complete truth, you need to go deeper, understand whether it is a compute problem or a memory problem, and then plan accordingly. Thank you.